go to our next topic, all right? Okay. By the way, let me just ask you, how many people have studied? So you have all learned logistic regression, right? Okay. So you know what logistic regression is. I just want to do a survey of background. Okay. So our next topic is classification. Now, in economics, we typically don't use the word classification, but it's a simple idea. It's the idea is if y is continuous, okay, y is continuous, it's called a regression. If y is discrete or categorical, like 1, 2, 3, okay, then it's classification. Okay, so classification is trying to classify y into 1 or 2 or 3. That's called a classification. We're going to discuss classification, this time, and we're going to begin. Oh, by the way, there are many classification problems in economics, right? If you are using a credit card, are you going to default? If you're going to default, it's a 0, 1, okay? Not defaulting 0, defaulting 1. Is this project going to be successful? 0, 1. Which product will consumer buy? Okay, suppose there are many car models. Which model will consumer buy? It's 1, 2, 3, 4, 5. Okay, so it's a Honda, it's a Mazda, right? So there are different models, and these are discrete. So this is also a classification problem. Which market will a firm enter? Okay, will a firm enter this market or that market? Will the firm enter into Fujian market, Xiamen market? This is a classification problem. Right? And finally, which political candidate will people vote for? It's a classical classification problem. Okay, this person is an Obama voter. This person is a Trump voter. This is a typical classification problem. We're going to begin with the simplest classification, which is called a binary classification. In binary classification, there are only 2 values of y. Okay, y has only 2 possible values. If y has only 2 possible values, okay, like y can only be a and a b, then there are 2 popular ways of labeling them. Okay, one is label them 0 and 1. Okay, so this is one way of labeling. The other is -1 and +1. Okay, so just we just give 2 different numbers, and our goal is try to classify them. Okay, classify A from B. Right? Okay. So how do we do it? Right? How do we do when y is discrete? What do we do? Well, there are 2 ways. So again, remember that if I give you an x, I want you to predict y. Remember, there are actually 3 ways. 2 is called discriminative, 1 is called generative, 2 is discriminative model. We're not going to talk about generative here, okay? Forget about generative. Let's focus on discriminative. There are 2 discriminative methods. The first discriminative method is I want to find out y given x first, and then from this, I can form a statement about y, right? That's the first way. The second way is I directly write y equal to fx plus e, and I directly find this fx. These are the 2 ways we said in introduction. So, in my last lecture on regression, we did what? We did the least square regression, okay? OLS. OLS linear regression is which method? Is this method or this method? It's the second method, right? We directly find an fx. We don't bother with probabilities. This is called a probabilistic model. It has to do with probability. Here, we don't care about probability. Now, we also introduced in linear regression. In regression, we also introduced a linear normal model, right? I hope you remember. We also introduced a linear normal model, in which case we assume y is equal to beta x plus e, but the e is a normal distribution of 0 and a sigma squared. Okay. Now, this is equivalent to y is equal to normal distribution with mean beta x and a sigma squared. So this is approach 1. Okay, so this is approach 1, where we care about probabilities. We estimate the probability of y given x first, and then we use it to do whatever we want. Okay, x by y. So this is a probabilistic model, and this is not a probabilistic model. Now we did both in regression, but we first talk about this, right? We do OLS first, and then we talk about linear normal models. Now, in classification, it turns out that we can have these 2 different approaches as well. Okay, we can do this or we can do this. I'm going to begin with this. Okay, this time I'm going to begin with this approach, and we're not going to talk about this one. Okay, so in classification, remember that remember that in classification, y if we have binary classification, then y is essentially 0 and a 1. Okay, y is essentially 0, 1. So my goal is to predict whether y will be 0 or y will be 1. So this approach, what this approach does, is I'm trying to estimate the probability of y equal to 1 given x first. Okay, I'm going to estimate this first. And if I have this probability, then I can basically try to predict whether y is 0 or 1. Okay? So how do I do it? Suppose I have estimated, right? Suppose I have estimated this probability. Then I can say, okay, if this probability is larger than what, I predict y equal to 1. If it's larger than what, I predict y equal to 0. What should I do here? If this is probability, so I've already estimated the probability. Then if this probability is larger than what value, should I predict y equal to 1? 0.1, 0.5? Very natural choice, right? Very natural choice, 0.5. If it's larger than 1/2, I say, okay, y is equal to 1. If it's smaller than 1/2, I say, okay, I predict y equal to 0. And that's based on what? That's based on the 0, 1 loss, right? 0, 1 loss. Remember, we can have different loss function that will give us different threshold, okay? Different threshold. But if we use 0, 1 loss, then we get 0.5 as a threshold. So that's going to be our approach. Our approach is we're going to estimate this first and use this p-value to predict y. That's our approach. What about the other approach? The other approach is, I just find the fx. So how do I do it? Well, I can do this, okay? So if this is x, 2x, so there's two-dimensional x, and there's some y. Okay, so there's some 0, 0, and there's some 1, 1, 1, 1, 1, right? 0, 1, okay? Then all I want to do is I want to find a boundary, okay, a decision boundary that helps separate them. And this boundary is my fx, okay? Is my fx. Right. A typical method for this is called a supported vector machine, okay? And SVM, right? So SVM is a typical method, supported vector machines. We don't have time to talk about it, okay, in this class. So basically, I will not talk about it, right? So we'll focus on this approach. We'll focus on this approach, right? Okay. Well, but it turns out that even if I use this approach, but let me just start first with a very simple question. So again, my goal is having give x, I want to predict y, but this y belongs to 0 and 1, right? Belong to 0, 1. The first question is, forget about probability, forget about first approach, second approach. Can I just run a linear regression like this? Can I just this? But y but there's only two values for y, right? Y has only 0 and 1. There are only two values. Can I just run a linear regression like this? Why not? Right? Some people say no. Why not? Well, the answer is you can. Okay. Yes, of course you can. You can do anything. Okay. So any model, it's all models are wrong, right? It's about which model is more useful. So the question, so of course you can do this. The question is this useful? Well, it's also useful sometimes. Okay. So let's ask this question. If I just do linear regression like this, O or less, okay? If I do O or less, what is my estimate? Okay, my estimated beta hat is an estimate of what? Is an estimate of EY given X, right? Right? Because I'm using what? Because I'm using L2 loss. So if I use an L2 loss, I'm trying to approximate the expectation function, right? EY given X. But what is EY given X in this case? In this case, Y is belong to 0, 1, okay? Y belong to 0, 1. If Y is 0, 1, what is EY given X? Is equal to what? Yeah. So look, Y has only two values, 0 and 1, right? So this thing is equal to what? This thing is equal to 0 times Py equal to 0, right? I'm going to forget about conditional X, okay? Just plus 1 times Py equal to 1, right? And this goes away, this goes away. So we're left with only probability Y equal to 1. So in other words, this is what? This is simply equal to probability of Y equal to 1 given X, right? So what I'm saying is if you run a linear regression, what you get, okay? What you get is an estimate of this probability, okay? Of probability, right? Okay. So of course you can use linear regression, of course, because again our approach is to estimate this probability first and use this probability to predict y, and the linear regression will give me this probability. Okay, because why? Because beta x is equal to expectation y given x, which will be equal to expectation probability y given x. Okay, so it should work to some degree. Okay, it should work. All right. Now, so in fact, this is what I'm going to do. Right. So I'm going to. By the way, so if you do linear regression, then this is your estimated probability. Okay. So this is beta x. This is estimated beta x. So estimated beta x goes this way. This is probability y equal to 1. This is the probability of y equal to 0, which is the inverse, right? So how do you make decisions? Well, you say, okay, if the y equal to 1 probability is larger than the probability of y equal to 0, then I'm going to say y equal to 1, right? Because when this blue line is larger than the red line, it is the probability of y equal to 1 is larger than 50%, 0.5. So I'm going to predict y equal to 1 here, and we're going to predict y equal to 0 here. Okay? Because here it's, the blue line is larger than red. So this green line is called a decision boundary. It's a boundary. Above here, y equal to 1. Below here, y equal to 0. That's what we do for linear models. And let's take a look at some data set, right? So this is voting data. And here the x variable is people's income, from low to high income. And the y variable is whether people have voted in the last election. Okay? Now, so there are two values, equal to 1 and equal to 0. Y equal to 1 means people have voted. Y equal to 0, people have not voted. So what you can see is you have data like this. Okay? So when people's income are low, many people have not voted. There are only some people who have voted when their income is very low. But when people's income increase, you see most people begin to vote. So there's a positive relationship between income and the vote. Okay, income vote. And what I'm going to do is I'm going to do a simple regression. I'm going to do a simple regression of voting behavior, vote or not, okay? Vote or not on income, okay? On income. Right? Beta, right? So beta income plus E, okay? Beta income plus E. I'm going to do a simple linear regression. Okay? And what I get is, something like this, right? This red line is what? Is my beta x, estimated beta x, okay? Beta hat x is my red line. And I'm going to say, okay, when this estimated beta x, which is my estimated probability of y given x, if this is larger than 50%, if this is larger than 0.5, I'm going to predict people is going to vote. If it's smaller than 0.5, I'm going to predict people do not vote. So the yellow point is the people is my prediction. Okay? So I predict these people vote, these people do not vote. These are my prediction. The blue line is the data, right? Now we can see is actually these are the mistake I make, because these people vote, but I predict them to not vote. Okay? And these people do not vote, but I predict them to vote. So these are my mistake. These are my predictions. Okay? These are my predictions. One thing you should note is the decision boundary is a linear one. Okay? It's a linear decision boundary because we're doing a linear model. Okay? And it gives you a linear decision boundary. What does a nonlinear decision boundary look like? Okay. Right. So here I have y equal to 1 and equal to 0. And I have some data here. Okay, I have some data here. I have some data here. Right? A linear decision boundary is something like this. Okay, something like this. It's like a linear line that says, okay, above here, I'm going to predict everybody to be y equal to 1. Below here, I'm going to predict everybody to be 0. And then it will make a mistake here, it will make a mistake here, right? A nonlinear decision boundary, could be something like this, okay? So that I, correctly classify these people as not voting, correctly classify people as voting. But we begin with a linear decision boundary model. Linear regression give you, if it's a linear in X, then it give you a linear boundary, okay? Give you a linear boundary. All right, now, what is the problem? So it looks like linear regression works, right? Looks like a linear regression works. It gives you this prediction, it's beta x. It gives you this prediction, and the prediction seems okay. It's not that bad. I make some mistakes, but you always make mistakes. So it looks like it's not a bad model. So do we use linear regression for classification problems? In reality, you probably don't want to do that. Okay, you probably don't want to do that. And the reason why, there are two reasons. Okay, and not the same two reasons that your old books, your old textbooks, or old professors may tell you. Okay, so one of the reasons is that oftentimes what we care about is not predict y. Oftentimes what we care about is we actually want to get the probability. So we are interested in the probability itself, not interested in predicting y. Okay, so if I'm only interested in probabilities, in estimating probabilities, then linear regression has a problem. Because why? Because this red line can go above 1, and it can go below 0. Okay, so give you a prediction, right? So remember that for linear regression, remember that beta x is your prediction, and this should equal to your prediction of y given x. Okay, this should equal to your prediction of y given x. But because this beta x is unbounded, okay, it can go above 1, it can go below 0, meaning that you will end up with a probability estimate that is either larger than 1 or smaller than 0. It's possible, and that's not good, because we want our probability to be between 0 and 1, right? Between 0 and 1. Okay. So if you care about probability, then this is not a good model for you. But if you only care about correctly classify y, meaning if you only care about correctly predicting y, then it should not bother you. Because if your beta x is larger than 1, I still classify y equal to 1. If it's smaller than 0, I still predict y equal to 0. Okay? So if you only care about making the best prediction, then this should not bother you. But if you're interested in the probability itself, then it should bother you. Okay, it should bother you, meaning you should change your method. That's the first reason. The second reason I will not talk about. I'm going to wait for a couple minutes and talk about. Okay, but there are two reasons why we do not want linear linear regression for classification. All right. So let's wait. Let's wait a couple minutes for the second reason. But let me just ask you a question now. The beta x is, I don't like this beta x because it can go above 1 and below 0. Meaning it gives me a bad estimate of probability if I care about probability. So if I care about probability, I want to estimate the probability of y equal to 1. What can I do? Like how do I do it? I do not want a linear model that gives me above 1 and below 0. I do not want that. I want something that gives me only something between 0 and 1, right? Okay, so I only want something between 0 and 1. So how do I do it? How do I do it? Well, let's think about this problem. Suppose, now the problem with the beta x is because it's a straight line that can go above 1 and below 0, okay? Can go above 1 and below 0. But I only want the value to be between 0 and 1 because I want to estimate the probability of y equal to 1. So is there any way for me to change beta x, okay, into something between 0 and 1? Now let me rephrase this question. Suppose I have a variable called z, okay? And the z is from minus infinity to plus infinity. Okay, z can be everywhere. How can I change this z into between 0 and 1? Okay, how can I change something, transform, right? How can I transform z from infinity, negative infinity, positive infinity, to between 0 and 1? How do I do it? Yeah, but how do I transform it? Like exactly how do I do it? Well, sorry? Standardize. Okay, all right, how to do it? Right? So that's why I asked at the beginning whether people have studied the logistical regression. How does logistical regression do it? I'm going to define a function. I call it sigma. It's actually called a sigmoid function. Okay? It's called a sigmoid. But I just call it sigma. I'm going to define the sigmoid function. Sigma z is equal to is equal to e to the z divided by 1 plus e to the z. And if I do that, then this thing becomes something between 0 and 1. actually, what does it look like? It looks like this is 1, this is 0. This look like something like this, right? Look at the S. Look at the S shape, right? So when z is really, really small, when z is negative infinity, okay? This is basically 0, right? This is basically 0. When z is positive infinity, it's basically 1, right? It's basically 1, okay? So this is 1, this is 0. I'm transforming what? I'm transforming, so this is z equal to 0. I'm transforming something that's from negative infinity to positive infinity. I'm transforming this into a function that's strictly between 0 and 1. That's called a sigmoid function. So you have seen this in logistic regression. If you ever wonder why do we do that, the reason is very simple. I just want to find a function that gives between 0 and 1. Okay? Now, if you can find another function that transforms z into between 0 and 1, then you can use another function. You don't have to use this. You don't have to use the sigmoid. All right? Okay? Now, in fact, I can also do something. So suppose, all right, suppose my y is, well, actually, no. We can talk about it later. Okay? But my point here is this is the reason why logistic regression has this form, because we want to transform it into between 0 and 1. Okay, now, in reality, so this is what we do. Okay? I'm going to say the probability of y equal to 1 given x. Okay? Now, this is a linear model. Right? This is a linear regression equal to beta x. I'm not going to say that. I'm going to say this probability is equal to not beta x anymore, because I want it to be between 0 and 1. So I'm going to say it's equal to sigma beta x. Right? I'm going to sigma beta. That's what, right? So beta x can still be this line. It's unbounded. I'm going to put a sigma on it so that it becomes something between 0 and 1. And this is logistic regression, okay? This is logistic. This is what you have studied in logistic regression, correct? I hope you recognize this, right? Okay. All right. How about, so what is the effect of beta? What is the effect of this beta? What happens when beta is large? What happens when beta is small? Now, let's see this, okay? So we have a 1 here, we have a 0 here, right? Okay, so this is x, we have x equal to 0. If beta, now the z is what? Z is, we just draw, it's an S shape, right? It's an S shape. If beta is really, really large, then when x change a little bit, I'm already 1, right? X change a little bit, I'm already 0. So it looks something like this, right? It looks something like this. What about when beta is really small? When beta is 0? When beta is close to 0? Then x can change a lot before what? Before it increases, right? So it looks like, right? It looks something like this. Actually, it should pass at 0.5, right? It looks something like this. In other words, when beta is small, this is almost a linear model. Okay, copy linear. Okay, so if you're in logistic regression, but if beta is small, it's basically a linear regression model. There's no difference. But if beta is large, then you get this, you get this really, really S shape. Okay, all right. Okay. Now, how do we estimate beta? Now remember that in linear regression, when we have y equal to beta x plus e, how do we estimate this beta? How do we estimate this beta? Well, you cannot estimate this beta without defining because this is just a linear model. How do we estimate beta? We use OLS method. But OLS method is what? It's actually not a method. OLS is a definition of a loss function. The loss function is L2, okay? Is L2. So you can write out a model first, but then you need to define your loss function. The loss function is L2. Then you can try to get what beta is. What beta is beta is what? Is x in x prime inverse x prime y, right? Okay. And this is a result if you minimize the L2 loss. How do we get beta here? How do we get beta here? Well, first of all, you define your loss function. What is a loss function? now we have a probability. Right? If you have probability, the loss function you should use. Do you remember? The loss function that we use for probability distributions is what? It's KL divergence. Okay? It's KL divergence. Or cross entropy. Okay? Cross entropy. Just another word. Same thing. Okay? All right, so we use cross entropy loss or KL divergence loss, which means if we minimize cross entropy or if we minimize KL, we are maximizing likelihood. So how do we estimate beta? We estimate beta by maximizing likelihood. Okay? So we use MLE. So the answer to how do we estimate beta is we use MLE to estimate beta. And MLE means we choose a beta to maximize the log of likelihood. The likelihood is this, okay? We choose the log of y equal to 1 given x, okay? If y equal to 1. If it's not y equal to 1, right? Okay. Right? So if y equal to 1, right? If we see y equal to 0, then the likelihood is 1 minus this p, right? 1. Okay, right? Right? So you times that, right? I should say, so it's essentially sigma beta x if y equal to 1, it's minus sigma beta x if y equal to 0, okay? Then you basically multiply them together, that gives you the likelihood function, okay? Maximum likelihood function. And you find the beta to maximize this likelihood, right? So if you see the likelihood function, okay? Okay? So you see the likelihood function, this is what the likelihood function is, okay? So, so if y equal to 1, then it's this one. Then sigma, right? If it's y equal to 1, if y equal to 1, then it's basically sigma, log sigma x. If y equal to 0, then it's this one. Okay? And you can combine them by simply having y and times y here and times 1 minus y here. Okay? Because, if y equal to 1, we get this, equal to 0, we get this. So this is the likelihood function. And what we need to do is to find the beta value to maximize this thing. Right? Now, how do you do it? You don't have to do it. Right? The software does this for you. But exactly how do you do it? There is no analytical solution. Just this is unlike linear regression. In OLS, we have analytical solution. We can just write down beta hat equal to this formula, right? Equal to the the least square formula. Here, there's no formula. There's no analytical solution. You have to find the beta yourself, right? Okay. So how do you find the beta yourself? Well, you have to, suppose this is what the likelihood function looks like. Sorry, the minus, okay? Minus the likelihood. It looks like something like this. When you maximize the likelihood, you minimize this thing, okay? This is the negative likelihood, which is basically KL divergence or cross entropy. So we try to find a minimum point this one, right? Now what you do is you start anywhere, like this, and you try to find your way to this point by, going this way. Look, okay, going this way, it's not good. Let me go this way. Good, okay, let me go this way. Good, let me go this way. Now in reality, you don't actually do this. We have many numerical algorithms that try to help you find this point, okay? Based on derivatives, based on gradients, okay? And based on Hessians, based on Jacobian information, there are many algorithms that help you find this point. But we're not going to study this in this course because you can just use the software. But you should remember that underlying your software is all these routines to help you find the minimum point. In other words, the thing I said the last time is estimation is optimization. Okay, so basically all estimation routine underlying is an optimization problem. That you have to define your loss function and find the minimum point. Okay, all right. Now in reality, what you can do is you can use R, right? So in R, you have this GLM function that help you do logistic regression. Why is it called GLM? Remember that the least square is LM in R. In logistic regression, it's called GLM. Why? We will talk about it, okay? But anyway, you can just do logistic regression on the same thing, right? On the same data, voting data. On the same voting data. So let me ask you this question then. Suppose I have successfully, right? Suppose I have successfully found my beta hat. Okay, I've succeeded finding the beta hat. Then how do I predict y? Okay, so remember that when I do linear regression, y equal to beta x plus e, I can find the beta hat. So if I find my beta hat, I can say, okay, if this beta hat x is larger than 0.5, I predict y equal to 1. Okay? If it's smaller than 0.5, I predict y equal to 0. This gives me a linear decision boundary, right? Remember? So here it's equal to 0, here it's equal to 1. Now, for logistical regression, once I get my beta hat, how do I predict y? How do I predict y? And the second question is the decision boundary linear or not? First of all, is this a linear model in X? It's not a linear model in X, right? Is this a linear model in X? It's not a linear model in X. It's a the sigmoid function is not linear. It's an S shape, right? It's a shape. But how about decision boundary? Is the decision boundary linear or nonlinear? Well, let's see, okay? So if I have beta hat, then what I do is my P is what? What is my P? My P is my sigma beta hat x, which is equal to e to the beta x, 1 over e to the beta x, okay? 1 to the beta x. And I should, but there's another way to write this, okay? There's another equivalent way to write this, which is, and I think you have seen this in your earlier textbook, which is log p y equal to 1 given x over p y equal to 0 given x equal to beta x. Right? Okay? Have you seen this? This is another way to write the regression. This is the same thing as this one, okay? Completely equivalent. Now, actually there's a function, there's a name for this function as well. So if you write log p 1 minus p, okay, there's a name for that. It's called a log odds, but it's also called a logit function. Okay, called logit function. But anyway, so I know this. So if I have my beta hat x, then I should do what? Then I should predict y equal to 1. I should predict y equal to 1 if beta hat x is larger than what? Is it larger than 0.5? No, it's larger than what? So if this one is larger than 0.5, this is smaller than 0.5, then this is larger than 1. Taking a log, this should be larger than what? 0, okay? Larger than 0, right? So if it's larger than 0, I get y equal to 1. If it's smaller than 0, I get y equal to 0. Okay, y equal to 0. In other words, the decision boundary, where is the decision boundary? The decision boundary is this thing equal to 0, right? This thing. Okay? So I basically did the same voting data. And this is what I do. This is what I see, okay? This is what I get. This red line is the logistic regression fit. Okay? So this is my estimate of the probability. It has this S-shaped, okay? And it's going to have a decision boundary here. And the decision boundary is still a linear decision boundary, okay? It is still a linear, why? Because the decision boundary is beta hat x equal to 0, which is linear in x. So I still get a linear decision boundary. Even though it's a nonlinear model, it gives me a linear decision boundary. That's why logistic regression is also often called a linear classification model. Even though it's not linear, it's called a linear classification model because it actually generates a linear decision boundary. Right? And I'm going to say, okay, these people vote, these people do not vote. This is going to be my prediction. Right? And I make these errors, okay? I make these errors. Now, compare this with linear regression. So this is logistic. We have seen linear regression results. How different are they? Well, here I classify everybody with income larger than 0.35 as 1. Below 0.5, 3.5 as 0. That's my result. How about linear regression? In linear regression, I predict everybody with income larger than 0.37 as 1. Below 3.7 as 0. So they're almost what? They're almost the same. Okay? So in this case, linear regression doesn't, logistic regression doesn't really give me much more than linear regression. Meaning you can actually use linear regression. Right? So why bother? Okay, why do we do logistic? There are two reasons. Like I said, there are two reasons. The first reason is what I've already said, which is I actually want the probability estimate. I not only care about classification, but I also care about getting the probability. Linear regression gives me probability above 1 and below 0, which is not good. Okay? So that's the first reason we want logistic regression. But there's a second reason. Okay? The second reason is this. If you only look at our little example here, logistic regression doesn't really give me much more than linear. But there's a very simple case which it will give me much more than linear, which is this example. Okay? Now we have some data like this. My goal is to classify y into red and blue. So if the blue is here, red is here, I have the same result. Okay, logistic regression, linear regression, completely the same, almost. But if I have some blue points here, then there's trouble. Okay, then there's trouble. Then the green line is logistic. This purple line is linear. And you can see the linear no longer works when I have some data here. Okay? Why? Why is that? Yes, it's because but why does OLS give you bad results? Actually, I think I talked about this last time. Yes, these are what? These are almost like outliers, right? So the problem here, the problem that linear regression doesn't give you good results here is because linear regression, especially because we do OLS. And because we do OLS, we use L2 loss. And if you use L2 loss, these points are far away. It's going to really change your fit. But should they change your fit? They should not. Because why? Because the true loss function, when you make classification decisions, the true loss function you should use is what? Is a 0-1 loss. Okay? Right? Now, meaning what? Okay. So let me give you this one. Right, suppose what does logistic regression do? Logistic regression estimate this p first, right? Estimate this probability first. And then based on this probability, it makes prediction. And so when you estimate this probability, so when you estimate this, you use KL divergence, right? You use KL divergence or cross entropy to estimate as a loss function to estimate this p. But once you have this already, the next step is predict y. And when you predict y based on this p, you use what? You use 0-1 loss. And what's the 0-1 loss? 0-1 loss is the true value. Okay, true value has 0-1, but you are going to predict y hat, right? You're going to predict y hat. So y hat is going to be 0-1. Okay, y hat is going to be 0. So if your prediction is correct, it's 0. If your prediction is incorrect, it's 1, right? That's the 0-1 loss. Okay, now what your y hat is, what is your y hat? Your y hat is based on the underlying probability, okay? It's based on the underlying probability. And the underlying probability is, is beta hat equal to x in terms of linear regression. In terms of logistic regression, it's this, okay? It's sigma beta hat x. Okay. The point is, as long as your prediction is correct, there's no loss. As long as your prediction is incorrect, okay? It should be 1, but you have 0, it's 1, right? It's 1. So the 0-1 loss doesn't care if your prediction is very incorrect or a little bit incorrect. As long as incorrect, there's only 1, right? Okay, it doesn't care how far away is it. If it's incorrect, it's 1. How about least square? Least square cares, okay? So in other words, if you use 0-1 loss, you do not care. So these are, we only care about making correctly predicting these people as blue and these people as red. You do not care about whether you're correct, how strong your prediction. You do not care about how far away it is, because it's 0-1 loss. Okay, so if it's incorrect, you have 1. Correct is 0. However, L2 loss really cares about how far away your prediction is from the true y. Okay, so the true y has 0-1, right? The true y only has 0-1, 2 values, but your predicted y hat could be like 2, 3, 5, 6, 7. So if your predicted y is really far away, you penalize it. You change your prediction. So your slope really changes. So the point here is L2 loss function is bad for classification, right? So it's not good to use L2 for classification, because in classification, you only care about getting the prediction correctly on the same side. You don't care about how far away it is. But L2 cares about how far away it is, and then it has a problem like this. That's one of the main reasons why you do not want to use linear regression for classification, okay? Because of this problem. Because L2 is not a good loss function for classification. Otherwise, okay, may as well use linear regression. Now, if you do not have this problem, okay, if you do not have outliers in a problem like this, then you get really, really close results. Okay, here you get really, really close results, in which case it's almost equal. Okay, all right. Okay, so our next problem is this. Now, it turns out that I've introduced logistic regression as a way to deal with y belong to 0, 1, right? Binary classification. That's how we introduce logistic. It turns out that logistic regression can deal with not only this kind of y, but can also deal with y like this. 0, 1, 2, 3, okay? Many 1. Now, in a particular setting, not always, but in particular. So let's think about it. Suppose this is all the data I have. 1, 2, 3, 4, 5. I only have five data points. Now, these 5 data points come from experiment in which, for example, we have a group of rats or animals exposed to some kind of chemicals. So this is the concentration of a chemical. This is how many animals, how many rats there are in the group, like 6. This is how many died. Okay? Y is how many died. So we have 6 rats, 6 animals in each group. Now, if the concentration gets really high, everybody dies. The concentration is low, nobody dies. Can I model this y? This y is not 0, 1. Okay? This y is not a 0, 1 variable. It's a 0, 1, 2 with a maximum of 6. Can I use logistic regression to model this? Yes. Why? Because logistic regression can be used to describe anything related to probability. So here we have what? We have corresponding to each concentration, we have a different probability of animals dying. So we can use logistic regression to model this probability. Okay, right? In fact, if you divide y by n, you get this p. But this p is not the underlying probability. This p is the realized percentage of animals that die. Now, if my goal is I want to know the underlying probability, then I can use logistic regression, because logistic regression is a way to model probabilities. Okay, so how do I do it? Well, let's come back to the y equal to 0, 1 case. Okay, suppose y is only 0, 1. Suppose y is only 0, 1. Now, logistic regression is y equal to 1. Okay, I'm going to forget about conditional x. Okay, but you know what I mean. Is equal to sigma beta x. That's the logistic regression. Is there any way to write it? Suppose I want to write y is equal to a distribution, okay? Some kind of distribution. What is the distribution of y? Now, I know this. This is what I know. Then what is the distribution of y? Sorry? What is distribution of y? So y is the probability, and y is 0, 1. And the probability of y equal to 1 is this. What is the distribution of y? Yeah, very good. Well, people say binomial, but you only have 0, 1. So it's a Bernoulli, right? Okay, so y is a Bernoulli distribution, okay? Y is a Bernoulli distribution. Now, Bernoulli distribution only takes a parameter called p, okay? So Bernoulli distribution is like a coin flip, right? You flip a coin, with a probability p, it becomes a head. So here, what is p? P is sigma beta x. Okay? So this is my logistic regression when y equal to 0, 1. Then how about here? What is this y? This y is the number of animals that die in the group. Each group has 6 animals. And this is how many they die. Now, we assume that underlying there's a probability that each animal die. This is the observed death. So what is the distribution of this y? What is the distribution of this y? Binomial, right? Very good, okay? So because binomial is just what? Binomial is just Bernoulli added together. Okay, so if we have n Bernoullis, we sum them together, that's a binomial. Okay, so we have a binomial distribution. We have a binomial distribution with n. N is equal to 6, okay? Right? N is just n. So we have n equal to 6. And then we have a p, and the p is equal to... we have a p, okay? We have binomial distribution and p. P is the underlying probability. Now, what is this model? It's just a binomial distribution, okay? There's no name for it. But if I write this p as sigma beta x, then this becomes a logistic regression. Okay? Right? So a logistic regression can be both a Bernoulli and a binomial. Okay? And then when it's a binomial, then we can use it to model y like this, which is like the outcome, the total outcome from a group, okay, with an underlying probability that's independent. Okay? All right, so if we do that, we can use logistic regression too, it turns out. And in R, so in R it's very simple. We have 6 groups. Well, sorry, 5. We have 5 groups. N is 6, 6, 6, 6, 6. Y is 0, 1, 4, 6, 6. And then you use the same GLM function to run a logistic regression. You just have to tell the GM function, these are the Ys that are died, and how big is this group size? Okay, what is the N? So if you tell them, then you can do a logistic regression, and it will give you the result. Okay, it will give you the result. Right. Okay. So I think I will just finish today here, and we can continue on Thursday. Okay, on Thursday. All right.